If Kubernetes feels like a foreign language, this is for you. Learn the essentials under 30 minutes and take control of your containerized applications with confidence. Hi there, great to see you and welcome back to my channel Codify with Subbu, a place to learn DevSecOps. In this Kubernetes tutorial, I will be traveling with you on a Kubernetes journey and we will learn Kubernetes from the startup. Are you excited? There's a lot of content we need to cover. Without further ado, let's get started. Docker made containers popular. It revolutionized the application deployment. Using the Docker technology and tools, application with its dependencies are packaged into a Docker image. Containers are created from this image. Containers are easy to run and manage locally. Imagine the task of managing hundreds and thousands of containers in production. Docker had many limitations when put into production, and hence the Docker Swarm emerged. Docker Swarm simplified the container orchestration services and supported scaling for simple to medium setups. Unfortunately, Docker Swarm was native to Docker and could not handle complex distributed systems. Kubernetes eliminates all these limitations, and Google Cloud is the birthplace of Kubernetes. Kubernetes is an open source container orchestration system for automating software deployment, scaling, and management. Kubernetes supports advanced orchestration, works across clouds, and the interesting fact is it was built for distributed workloads. Automatically adjust the number of running pods based on demand. Ensures application is always running by automatically restarting the failed pods or moving the load to a healthy node. Prevents over or underutilization of resources such as memory and CPU. Seamless deployment, scaling, and updates with minimal manual effort. Monitors pods and automatically replace or restart them if they crash or become unresponsive. Allows rolling out application updates without downtime. Automatically routes traffic to the right pods, distributing the load evenly for better performance. Hides the complexity of the underlying infrastructure, allowing to focus on application development. Supports plugins, custom resources, and integration with CI/CD pipelines, monitoring tools, and more. Enables applications to run seamlessly across different cloud providers or on-premise infrastructure. Kubernetes maintains the desired state of the application by using declarative configuration. Pod is the smallest deployable unit in Kubernetes. Pod contains a group of containers working together, a main container and one or more sidecar or helper containers. Containers inside a pod share the same IP address and also share storage resources. A pod is ephemeral, and if it crashes, Kubernetes restarts the entire pod. This means we cannot communicate with the pod through its IP address. Question is, how do we communicate with the pod? Kubernetes service is the way. Kubernetes service is an abstraction that allows pods to be accessed by other components. It might be inside or outside the cluster. It provides a stable network endpoint for accessing a set of pods, even if the pod's IP address changes. Also, Kubernetes service object is used to load balance the request between pods. Ingress in Kubernetes is a resource that manages external web traffic and routes it to a specific service within the Kubernetes cluster. It acts as a traffic controller, routing web traffic to the correct service based on defined rules. Config map and secrets are Kubernetes resources that is used to pass configuration data to the application. Config map is a Kubernetes object used to store non-sensitive configuration data. Secret is a Kubernetes resource used to store sensitive data. Persistent volumes and persistent volume claims are Kubernetes resources for managing storage in a cluster. Together, they decouple storage management from application management making it easier to handle the storage needs. Persistent volume or PV maps to a physical storage and is managed by Kubernetes. A PV is available to any pod in the cluster. It is provisioned by the administrator manually or dynamically through a storage class. PVC is how pods request the storage in Kubernetes. It claims a specific amount of storage with certain characteristics from the available persistent volumes in the cluster. Pods use the persistent volume claims to access storage without worrying about the underlying persistent volume. Let us now see how PV and PVCs work together. Admin creates a persistent volume manually or dynamically using the storage class. Then a persistent volume claim is created. Kubernetes then matches the PVC to PV. Finally, the pod uses the persistent volume claim. Imagine we have a web application. We want 3 instances of the application running for reliability. If we release a new version, we want to update the application without the downtime. If a pod crashes, it should be automatically replaced. If traffic increases, we can scale up the number of pods. All these requirements are met by Kubernetes deployment. Then, what is a deployment? Deployment is a Kubernetes object that manages the lifecycle of an application. It ensures that the application is running in the desired state and it automates tasks such as scaling, updating, and self-healing of the application instances. Under the hood, a deployment uses a replica set to maintain the specified number of pods for the application. Kubernetes architecture consists of master nodes or control plane and worker nodes, which work together to orchestrate application deployment, scaling, and management. Whatever you are seeing on my screen is a high available architecture. To make things simpler, I will walk through a simple Kubernetes architecture containing 1 master node and 2 worker nodes. Master node or the control plane manages the entire cluster. Control plane has multiple components. API server is the gateway to the Kubernetes cluster. It exposes the Kubernetes API, which is used by the kubectl command line interface. Controller manager ensures the cluster is in the desired state by monitoring and responding to changes. It restarts the pods if required for self-healing. Scheduler assigns pod to specific worker nodes based on resource availability and requirements. HCD is the brain of Kubernetes, storing all cluster state and configuration data in a distributed key value store. Worker nodes runs the application workloads as pods. Kubelet is an agent that runs on every worker node in a Kubernetes cluster. It is responsible for ensuring that the containers in a pod are running and healthy according to the specifications provided by the Kubernetes control plane. Container Runtime Interface or CRI is an API standard that defines how Kubernetes interacts with the container runtimes. Kubernetes uses the CRI to manage our containers in a uniform and decoupled way, making it possible to use different container runtimes. kubeproxy is a networking component that runs on every worker node in a Kubernetes cluster. It manages network connectivity and routing for pods, ensuring that services can communicate internally and externally within the cluster. I was not sure where to fit in the pod networking in the Kubernetes architecture and thought it might be good to have a section by itself. Pod networking is possible through the Container Network Interface or CNI plugin. There are a lot of plugins in the market. It provides networking capabilities and ensures that pods can communicate with each other within a node and across nodes if necessary. In the next section, we will see how everything works together in the Kubernetes architecture. Let's say, as an Kubernetes admin, Bob wants to deploy 3 instances of a web app using a container image. Bob creates the deployment manifest file. He submits the request to the Kubernetes cluster using the kubectl command. The kubectl command interacts with the API server. API server receives the request, validates it, and stores the desired state in the etcd data store. Scheduler checks the cluster's available worker nodes and assigns pods to specific nodes based on resource requirements. Kubelet on each worker node communicates with the API server and creates the assigned pods on its node. Container runtime pulls the required container images and starts the containers. Kubeproxy sets up networking to route traffic between pods, services, and external users. If external access is required, ingress manages web traffic and routes it to the appropriate service. Controller manager monitors the cluster state. If a pod crashes, it creates a new pod. If a node becomes unavailable, it reschedules pods on other nodes. Look at this, 96% of my viewers have not yet subscribed to my channel. If this video helped you in understanding Kubernetes, hit the like button, drop a comment with your biggest takeaway, and of course, subscribe to my channel. Thank you so much for watching this video.